Okay, thank you so much, Kent. It's great to be here or back. We were here 4 years ago. That was before we made some of the advances that we're going to show in this talk. So it's really exciting to come back and talk about it again. I'm Professor Smith, and this is Professor Lovelace. We're going to switch off in the talk. I'm an experimenter, and he's a theorist, so I can answer the hard questions maybe about the experiment, and he can answer all the hard questions about space-time and black holes and wormholes and anything like that. Just go ahead and ask him. We're both professors just down the road at Cal State Fullerton. We both live in Fullerton, and you might see us out in the parks walking around our babies, or our kids. Mine is 2.5 and his is 1. So we're really happy to be giving a talk right here in Fullerton. The picture that I'm showing here is an artist's rendition. It's actually an artist from Sonoma State University here in California, an artist's rendition of the explosion that happens in light, but also in curved space-time when 2 neutron stars crash together. And this was something that we observed in 2017 last year. So I'll say a couple of things. We're funded by the National Science Foundation and the Research Corporation for Science Advancement. We have a center called the Gravitational Wave Physics and Astronomy Center with this neat logo. We're at Cal State Fullerton, and we're members of the LIGO Scientific Collaboration, which I'll talk a little bit more about later. This is a little shot of our group, all gathered around this summer doing research. There's a lot of Fullertonians in the group. It sounds like actually some of the people in the photo may have relatives in the audience. We have 4 professors and 1 postdoc, so 5 people with PhDs, and we have a lot of undergraduates, high school students, summer interns, and master's students working in the group. Normally we have about 20 to 30 people in the group at any time of year, sometimes a little less, sometimes a little more because of people graduating. We do research, but also education and outreach and gravitational wave science. What's a gravitational wave? We'll talk about that in a moment. We also have some software developers because we do a lot of our work on computers. Over the years, we've graduated a bunch of students as alumni. Many of them are in PhD programs in places like MIT, Caltech, all around the nation, Syracuse University out east. So this is our group, and we also want to acknowledge that we get some funding from individuals which supported our center. So in addition to outreach and education, we also really think that one of our roles as educators is training the next generation of scientists, so training young people to make future discoveries. I think we have a few of folks that will be joining the ranks of scientists in the future right here in the audience, and relatives of other ones, and it's going to be really exciting for us to see what kind of discoveries you all make in the future. Here's just a few pictures of some of our students getting involved, some in the lab, some on computers, some putting together computers, which is like a combination of labs. This is our weekly group meeting where we sit together and discuss black holes and neutron stars and the topics that we're working on. And here are some of our students going out to conferences and presenting. Those are some of the things you might do if you joined our group eventually at Cal State Fullerton or similar groups around the world. Okay, so now I'm going to switch to Jeffrey, and he's going to introduce you to how to observe the universe. Maybe I'll stay over here.
Okay, so to start out with, I wanted to just take a step back. We're going to be talking about a new kind of astronomy, so I thought I'd start by saying something about the ordinary kind of astronomy. So to help you see what's exciting about gravitational wave astronomy, let me start out by showing you the big picture of the universe. So this is the Earth. Oops. This is the Earth. The Earth is a sphere, but you can unfold it in a map in a whole bunch of different ways, and there are map nerds who can argue on the internet about which one is best. This is just one that I picked because it was simple, and so this is showing the entire surface of the Earth at once. Now imagine instead of looking down at the Earth, you flip all the cameras around so you're looking up, outwards, into the universe, out into the night sky. Then the night sky looks like this. So, it's pretty dark. If you had a lot less lights than you have around here, you might be able to see the Milky Way. It won't look bright like this. You would need a long exposure camera to see something like this. And you'll see some stars and galaxies, some planets. We can see a few planets directly that aren't orbiting the sun, but most of them are right here in the solar system. That's what the universe looks like when we think about space. This kind of thing is what you picture. But this is just in this narrow part of light that our eyes are able to see. If you were to look at the universe with different kinds of light, different colors, redder than we can see or bluer than we can see, the night sky can look very different. So this is what the night sky looks like in a certain color of microwaves. So there's some stuff you can see in the center of the galaxy, but there's also just this one color. I mean, it's not something we can see, so you just sort of pick something. So the people who made this picture just picked green. But there's some color of microwaves that's the same brightness, same color, just coming at us from all around us. This is light that's left over from the beginning of the universe. It's called the cosmic microwave background radiation. So in this particular color of light, the sky doesn't look dark at night at all, in the same way, where there's just little points of light. The light is all spread out. This is an infrared view of the night sky, a little redder than what we can see. And this is dust. The blue stuff here is dust inside the solar system. This is the center of the galaxy that we're in again. And then this red dust here is left over from stars that were made a long time ago. So again, it looks really, I mean, these colors are all fake because we can't really see them, but this just to give you a feel that the sky looks very different. This is X-rays, and X-rays, this view of the sky was impossible until we could launch things into space, because it turns out the atmosphere blocks X-rays. So even if you had X-ray vision like Superman, if you look up, you wouldn't be able to see this. You have to actually launch satellites. And when they first launched satellites and saw X-rays, at first they were afraid it might be something going on with, with the Russians doing something with nuclear weapons, but it turns out they were X-rays coming from space. Some of them, these are X-rays from things like black holes. You can't see black holes, they're black, but when matter falls in, it can get hot and glow, like hot metal can glow. And so that's what some of these points here are. These are like X-rays, but even more energetic. In gamma rays, you can see things like, the sun shows up on here, but you can also see things like neutron stars, these giant atomic nuclei in space, like a nucleus of an atom, but the size of a city. And every once in a while, there will be a bright flash in the night sky of these very energetic light waves. And it was thought for a long time, well, maybe this could be caused by two neutron stars crashing into each other. We'll come back to that a little bit later. But what we want to talk about is, what about the things you can't see? You see all different kinds of things in the universe with light. But all we know about the universe outside the solar system until now came from light. And so anything that was dark, it was very hard to learn anything about. So what we would like is a new sense, something other than light that we can not exactly see, but sense out in the universe, what else might be out there. There's one other force besides electricity and magnetism, which light is made of, that can do that, and that's gravity. So what we're going to talk about is a new kind of astronomy to try to go after things that either are completely invisible or that might have visible light, but also be very bright in this new sense that humans have just gotten. And so that's gravitational waves. So Josh is going to tell us about gravitational waves, and I'll come back and crash the talk again in a bit.
All right. So gravitational waves, this new way to look at things using gravity, has only been accessible to us relatively recently. But it's been known since around 1915. So this is a picture of Albert Einstein. My wife and I are actually watching the Einstein documentary right now on I think it was the National Geographic one, Einstein Genius. It's really good, almost done, no spoilers. So Einstein developed the theory of general relativity. So special relativity said E equals mc squared, and nothing can travel faster than the speed of light. But he was a little bit disappointed in its limited ability to capture everything, so he extended that to general relativity, which captured gravity. General relativity is more accurate than Newton's version of gravity. So Newton said if you have two objects with mass 1 and mass 2, you can calculate the force between them by doing mass 1 times mass 2 over the distance between them squared. And Einstein's theory is more accurate because it includes the aspects from special relativity, but it says that, especially for strong gravity and high velocity, that we have to think of gravity as an effect of the curvature of space-time. John Wheeler put this more snappily, saying matter, so something like the sun, tells space-time how to curve. If you take an object like the sun, you can imagine that space and time is like a rubber mat. You put something like the sun, like a bowling ball, down in that rubber mat, it curves. And then space-time, which is now curved, tells the matter how to move. If you have a bowling ball and you throw in a marble, the curved mat makes the marble deflect and maybe come into an orbit. And so it's that curvature that tells objects how to move, not the force that Newton had calculated with his force equation. And the sun is one level of curving space-time, but you can get much more extreme than that. You can have extreme curvature, gravity that is so strong that not even light can escape from that. And that's what you have in a black hole. A black hole would look sort of spherical, although we wouldn't be able to see the surface. Here we've colored the horizon of the black hole green. And this isn't a true horizon. You could pass through it. The problem is that you could never come back, because nothing from within this horizon, even the most elusive particle out there, light, can escape. Nothing can escape. So inside this horizon, the black hole has mass, but it's all been compacted down to a singularity where the gravity is infinitely strong and all the mass is in that tiny, tiny point. And if we imagine taking a cross-section across the horizon here and showing that same sort of diagram for the curvature of space-time, it would look curved like this, but then there would be a part at the bottom which corresponds to this green surface that's cut out. And so if you threw in your marble and it went past this hole, it would never come back. Very similar to these coin things that you see in the mall. You put in the quarter. Once it goes through there, the mall's got your quarter. It's never coming back. Black holes used to be stars. So they used to be bright, luminous stars. And after those stars ran out of fuel and collapsed, they formed black holes. So black holes are dead stars. Another type of very compact object, not as compact as a black hole, but the gravity's last stand against becoming a black hole, is a star called a neutron star, where it's compacted so much that it's formed almost entirely of neutral particles that don't have repulsive forces with one another, neutrons. So this is a picture of Fullerton, and this is a 2-scale picture of the size that a 1.5 times the mass of the sun neutron star would have, and the size of a 1.5 times the mass of the sun black hole would have. So we could easily fit a black hole or a neutron star right between Fullerton and Yorba Linda, but it has a mass and a half, a 1.5 times the mass of the sun, so it would destroy the entire solar system. That's one downside. So black holes and neutron stars curve gravity so strongly that they can hold objects in orbit around them. And so here's some marbles, and this is at Astro Camp in Idlewild, California. Maybe some of you have gone to that or seen that before. And I was there looking at their demonstration. And so I have a question for you. We started all these marbles going around, and now they all ended up at the center. So what causes those marbles to spin down and come down to the center and end up touching this sun? Yes, back there.
Gravity.
Okay, gravity. That's definitely a part of it.
Centrifugal force.
Okay, got another one here.
The curve is causing the gravitational pull affecting the marbles, which causing the...
Okay, so I'm with you both on that. The curve and the gravity. The curve is causing the gravitational pull, so gravity and the curvature, and those are causing the marbles to go around in the orbits. But if you had something like the sun, those marbles would continue going around, or in a black hole. Like our marble, the Earth, continues to go around in an orbit nice and stably. But these ones somehow spiral into the center. So the gravity causes them to orbit, but what causes them to move into the center? Yes?
I'd say either the orbit is unstable or friction.
Okay, so either the orbit is unstable or friction. I'm going to choose the simpler one, the second one. So I think in this case there's a lot of friction, because this mat is made out of some material. If you were there listening to it, you'd hear some sounds. There's air. So these marbles are losing energy to friction because they're slowing down as they roll around. If you roll a ball on the floor in this carpet, which is a similar situation, it will eventually slow down. So those are all great inputs. It's the gravity that's causing them to go in the orbits, and it's the friction that's causing them to come in there. And friction is a loss of energy. So if you have something that's losing energy while it orbits, its orbit is going to get smaller and smaller. So now let's use that to look at the idea of gravitational waves. This is a diagram similar to the ones that we looked at before of two black holes, where the curvature of space-time is really strong here and their light would be unable to escape. As these two black holes orbit each other, you're going to see that the space-time around them has ripples in it. And this is a simulation done by Nick Damos, who's now a PhD student at MIT, but was an undergraduate student at Cal State Fullerton. And Jeffrey's team works on these numerical simulations of black holes. So as the two black holes orbit around each other, they get closer and closer, and the space-time gets stirred up, and it makes 1, 2, 3, 4, 5, 6, 7 strong gravitational waves that spread out from that. So gravitational waves are ripples in the fabric of space-time. It's like if you put your finger in a pond and moved it around, you could make ripples going away in the pond, and then somewhere far away, someone could see those ripples and say, oh, I think somebody was moving over there. I think I saw a fish or something like that. Here, it's I think I might have seen a black hole because I saw 7 of those ripples. And that's gravitational waves that we study in our center. So here's what gravitational waves are. They're those ripples that go across in space-time when massive objects move around each other. So they're ripples in space-time. They travel at the speed of light. That was a theory, but now we have experimental evidence. They are generated when objects orbit each other or if they explode. They travel through the universe without being blocked by dust, gas, or galaxies. So the pictures that Jeffrey showed you that we use light to see, light can be blocked by things like planets and dust and other objects. So we can't see light from the very center of the galaxy or from very far away galaxies very well because of that. Gravitational waves can't be jammed. If you had a gravitational wave phone and a gravitational wave receiver, you could get gravitational waves to the deepest parts of the Earth or through any objects. So because they're so different than light, they don't work on electricity and magnetism, they work on gravity. They allow us to see astronomy that wouldn't be accessible by light. For example, black holes that would be entirely dark to light look bright when we look at them with gravitational waves. It's an entirely new sense for us to use as humanity. And this means there's also an entirely new spectrum with all different wavelengths, just as there was in light, but this entirely new sense comes with its own different wavelengths to look at. So Einstein, coming back to him, he, in 1916, wrote papers which showed that there should be gravitational waves. And this one is called the Near Field Integration of the Field Equations of Gravitation by Albert Einstein. And in here, he did some calculations, and I translated some of this. And he said, if you do the calculations, one obtains the radiated energy of the system per unit time with gravitational waves. And you see that in all conceivable situations, that it must have a practically vanishing value. So in 1916, all conceivable situations that Einstein could conceive of, gravitational waves should be practically vanishing. Vanishing is a very interesting physics word, which means like approaching zero, getting very, very small. But he didn't say they would be zero, and he also said in conceivable situations. So what's changed since 1916? Since 1916, a lot of things have advanced. One of the things is that we've developed lasers, which are amazing measurement devices, pretty inconceivable maybe in the day of Einstein. And the second is that we now know that there are giant black holes crashing into each other out there in space, which was also something that Einstein might not have thought about when thinking about what was conceivable. Why did Einstein think measuring gravitational waves was inconceivable? To look at this, we have to look at what gravitational waves do. Imagine that you have a few different objects out in space, and this is some sort of space-time that we're looking at here. And imagine that we're generating gravitational waves from black holes right here. So there's waves of gravity going into the board. If I start this going, what waves of gravity do, if you're sitting there, is they will stretch you to make you tall, and then squeeze you to make you short. And while they're making you tall, they'll also make you thin. And while they're making you short, they'll also make you thick. And so over and over again, the gravitational wave passing will stretch and squeeze the distances between objects. Now, why did Einstein think we couldn't measure that? The reason is that the fractional change I'm showing you in this video is 1 square out of 10, so about 10%. The fractional change that we get when two black holes crash together out in space is 10 to the minus 21. So this is scientific notation, and that means we have to take 1% or 10%, and we have to add 20 zeros. We have to have the period and add 20 zeros to it. So it's incredibly small. Suppose that we had a 4-kilometer distance here. How much would it stretch? So 4 kilometers, the reason we do that is that's the length of the detector we actually use, so that's why I'm using that number. This length would actually be changing by 10 to the minus 18 meters. I'll tell you in a second, that's 1,000th the width of a proton. So if I made the video move by 1,000th the width of a proton, it would be a pretty boring video. I don't think anyone in here, maybe Superman or someone could detect that change, but I certainly couldn't. So really, how small is 10 to the minus 18 meters, and how could we possibly measure it? 1 meter is a human height, roughly. I'm almost 2, but give or take. A human hair would be 1/10,000th the height of me. And if you divide that by another 100, that's the wavelength of light, which is around a micron. If you divide that by 10,000, that's the size of an atom. And if you divide that by 100,000, that's the size of a proton in the nucleus of an atom with the electron cloud around it. So that's pretty small, but then you have to divide that by 1,000 to get to 10 to the minus 18 meters, which is how big of an effect a gravitational wave makes when it passes through a 4-kilometer long detector. So it's a really small number, and this is why Einstein didn't think it was possible to detect it. So what is, I mentioned some of the advances that have happened since Einstein's time. One of the major ones is a laser. So a laser is a very, very accurate measurement device. Just this week, 2 men and a woman won the Nobel Prize in Physics for development of laser technology. There have also been other Nobel Prizes awarded for lasers. Lasers are incredibly useful in modern technology. So here's a laser, and this is a partially coated mirror, like a windshield, which reflects 50% of the light and transmits 50% of the light. And then this thing over here is a detector. So this is a simplified view of the detectors that we use to measure gravitational waves. The light comes out, it's a wave, it gets split along the yellow arm and reflected off this mirror, and then it gets split into the blue arm. The blue arm and the yellow arm beams come back together and they come over here. We hold the arms so that the waves are exactly out of phase. So a peak doesn't line up with a peak, it lines up with a trough. If a gravitational wave comes, it stretches and squeezes space-time. That makes one arm longer and the other arm shorter, which means the cancellation isn't perfect. Over here on our photodetector, we get some light, no light, some light, no light, as that gravitational wave passes through. So this is a way to transform changes in space-time, you getting taller and shorter, into light on a photodetector that we can then hook up to some electronics to measure a signal to say we saw a gravitational wave. All right, and this instrument is called a Michelson interferometer, after Albert Michelson, who here in California made measurements with this device quite some time ago. So that's the simplified version of what the Laser Interferometer Gravitational Wave Observatory is. This is a picture from a movie called LIGO Detection, which is a documentary that was partially filmed also at Cal State Fullerton. So if you want to look into that LIGO detection, this is just one snippet of that shows what LIGO really looks like. And this is LIGO Hanford. We were there recently with some students, and they're going to take us on a little tour here. So first of all, we're up in a plane looking down at LIGO Hanford. Now we're going to go to the AutoCAD version of the drawing, architectural drawing version of that. This is the main building. These are vacuum chambers. Over here in this vacuum chamber is the very beginning of that optical setup. There's a giant laser with 200 watts of optical power. And that laser beam comes in and it passes through some components. These components adjust the shape and the frequency of the laser so that it's like a perfect sinusoidal wave. After that, it goes into some components that are adjusting the size of that beam and that are going to reflect it multiple times to make the laser even stronger. This is that beam splitter that I said is like your windshield, where some light goes through and some light bounces off. And then when the light goes through, it travels all the way down those 4-kilometer-long arms to bounce off mirrors that are way down in the other end station. So sometimes I jog down those arms when I go visit, so you can do an 8K just by going down and back once. And the light goes down and back a lot faster than I do, and it bounces back and forth many, many times and builds up its power in something called an optical cavity. So this is a trip down to the end station where one of the mirrors is hung. It's hung as a pendulum, so there are thin wires which go all the way up, and it has multiple stages, and this is the final mirror here, and this is all done to suspend it and isolate it from the vibrations of the Earth, so it's very, very still. And that's the same with these mirrors here in the central building. As the light comes back from those two arms, it recombines, and finally we get it down here where we're going to look with our photodiode. There's some other optics which take the big beam and bring it back down to a small beam, and then they adjust its shape again, and they put it onto photodiodes. And so when the gravitational wave comes and it stretches and squeezes those distances, that photodiode measures the signal of a gravitational wave. So that's a lot more advanced version than the first one that I showed. So when you build a scientific instrument, it's not going to be infinitely sensitive. You wouldn't be able to measure everything with it. It's going to have some limitations. So what are the limitations that we have in LIGO right now, the Laser Interferometer Gravitational Wave Observatory? First, I said the ground is always shaking. You can feel it when you're sitting there. You move around, trucks are driving outside, the air is blowing, earthquakes happen in the world and they ring off the Earth like a bell, and this shakes the ground. Our mirrors are connected to the ground, but we isolate them by hanging them from thin wires so that if the ground moves a lot, the pendulums move a lot less. Those mirrors that are suspended there are made of atoms, and atoms that have temperature move around. So when you have a higher temperature, that means that the atoms inside of you have a higher energy, that they're moving faster. Anything at any temperature above absolute zero is moving around, and we call this thermal motion. And that moving around of the atoms is actually enough to disturb our measurements. And it turns out that light isn't a nice wave like I showed, but it's also has a quantum nature, and it's composed of particles. If we try to measure the light in our photodetector, it won't just simply go light to dark. It'll be kind of jumpy and in between, like rain falling on a roof. Great day to make that analogy, I guess, with the rain, a little bit of rain, because the detector is measuring photons as they fall on the output. So we have 2 of these in the United States, and 1 of them in Italy, and a few other detectors that are in some form of coming into operation around the world. And this is our international network of detectors that we use to measure gravitational waves. Okay, so now I'm going to switch back to Jeffrey, and he's going to hit the exciting part.
Okay, so I want to tell you about some of the things that we've seen. Up until now, what we've told you, we could have told you back in 2014 when we were here. This is what we saw. So the first thing that I'll tell you about is shown in this little animation. Now let me walk you through this. So this is fractions of a second. So from here to here is about 1/5 of a second. That's about how long it takes you to blink once. So this whole thing that we're showing you here is about 1 blink long. Vertically, this is showing you frequency. So this is the pitch that these waves would have if you plugged speakers into your electronics. They're not really sound, but if you plug speakers into the output of your instrument, the frequencies are frequencies we can hear. And it sounds sort of like a whoop, but it starts out low and quieter and gets higher pitched and louder, like whoop. But it happened very fast, faster than just a fraction of a second. This is the first gravitational wave that anyone ever observed before. This happened in September 2015. It was 1 day less than a month after I got married in 2015. And I'll say afterwards, my wife was very patient and understanding how late I was staying up working on stuff related to this. So let me walk you through what this wave was doing. So I'm showing 2 curves here. One of them, the pink curve, is is going to show you the stretching and squeezing of space and time at the detector in Hanford, Washington, up in a nuclear waste site. The light blue curve is showing the stretching and squeezing at the Livingston, Louisiana detector. It's down here in a swamp in Louisiana. So I'm not sure exactly how they decided where they put them, but I think Congress had some input on it. So that's but we're fortunate that they decided to put two detectors far apart, because we can time the difference in the waves arriving at one or the other to try to tell where they come from on the sky. So that's what the two curves are. Now, what are they showing you? So this is time in those same units. It's like from 0 to 1 eye blink worth of time. And then I'm showing the stretching and squeezing up and down. But in order to make the stretching and squeezing go between plus and minus 1, I didn't just have to multiply it by 10, like with that 10% squeezing in the movie I showed you. I had to multiply it by this sort of obnoxiously big number here. At the beginning, these curves don't agree at all. This is just noise in the detector. We can't get rid of the noise in the detector. We can only try to make it as small as we can. But once you get to about here, you can start seeing the pink and the blue curves start doing the same thing. They're following each other. This gives us confidence that it's not some local disturbance. Two detectors in two different states on opposite ends of the country are seeing the same wave pattern. So that tells us that we saw a gravitational wave in September 2015 from space. By looking at the pattern in the wave, you can try to figure out, well, what created it? So this yellow curve is a computer calculation that my students and I did on our big computer at Cal State Fullerton. And this particular calculation has two black holes going around and around each other, losing energy, not to friction, but to sending out these gravitational waves. And then, and so, you know, back here where the detector's swamped by noise, they don't really agree well. But this yellow curve starts tracking and agreeing very well with the observed signal. And that's just a first cut at giving you an idea of how you could guess that these waves came from colliding black holes. By looking much more precisely and doing fancier math than I showed you there, it's a lot fancier than just just laying curves on top of each other. You can learn what the source of the gravitational wave was like. It looks like the kind of wave from two very massive things going around each other. And if you look at the spacing between the peaks of the waves and exactly how it's getting narrower and narrower, that tells you, that encodes how massive each of those objects were. And it tells us that one of them was about 31 times the mass of the sun, and one was about 39 times the mass of the sun. The computer calculation solving Einstein's equations, when you put in a 31 and 39 solar mass black hole and let them go around each other, it tells you that they reach a quarter of the speed of light just before they merge into this sort of potato-shaped black hole. But black holes don't like being potato-shaped. This is the horizon after it's been created, and then it rings the same way if you hit a drum or a bell, and it rings as it quiets back down. The surface of the black hole does that too. And it left behind, according to the computer calculations, a 67 solar mass black hole. Now, if any of you look at the numbers here, you might notice something isn't quite adding up there. We started out with 70 and ended with 67. Where did 3 suns worth of mass go? It all got completely obliterated and converted into gravitational wave energy. For comparison, I don't know if any of you ever drive down the 5. You know, there used to be this nuclear station there that was, I think it's turned off now, but it used to make electricity. When it was running, it would convert a couple pounds of mass into energy every year. This is converting 3 suns worth of mass into energy in just a fraction of a second. In the nerdy physicist sense of power, which is energy divided by time, this is the most powerful event that humans had ever seen before. Except we didn't exactly see it, we just used our new sense, picking up gravitational waves to observe it.
Jeremy.
Question.
Oh, yes.
You've got about four things that are where they come together.
Yeah.
Does that represent 4 rotations as they're coming closer together?
That's a wonderful question. You're on the right track, but there's just a factor of 2 there. It turns out when the black holes go around each other once, you get 2 complete cycles of the waves.
Oh, okay.
There's some deep reasons for this that has to do with we think gravity is carried by a particle called a graviton, and it's specific properties tend to make it do that. Light behaves differently. If it were light, it'd be sort of 1 cycle per orbit, but with gravity, it's 2. So, but your intuition is basically right. It's just 1 cycle here is only half an orbit.
Okay.
That's a great question. Okay, so the one last thing you can infer from this, from measuring the waves very precisely, the computer's calculations can tell us, according to Einstein equations, right by the black holes, if you had the misfortune of being right next to them, how strongly you would be stretched and squeezed. And it could be even more than that 1/10 you were seeing. And actually being stretched by that much is not comfortable. In fact, yeah, it's worse than not comfortable, it's fatal. This kind of stretching and squeezing can not just destroy you and pull you apart, it can even pull stars apart. And we'll see a little bit of that later. And yet, it's so faint when it gets to us, this tiny, tiny thousandth of a proton motion. It turns out that all waves get dimmer as you get farther away. Like if you look at light from far away, it looks dimmer. And by exactly how much dimmer, we can figure out that this black hole pair colliding was 1 billion light years away. And because the waves travel at the speed of light, that tells us that they took 1 billion years traveling through the universe to get to Earth. And they just we had the fortune that they got to Earth right after our detectors turned on for the first time. So that tells us, back at the beginning, 1 billion light years away, 2 black holes collided, and then just in time, we saw them. Now that's not the only thing. Now, the computer calculation doesn't just tell you what the waves look like, how they would affect a detector. This is from the same computation. It shows you if you were up close and had a slow motion video, like take a slow motion video with your phone, except maybe 100 times slower instead of 2 times slower, this is what you would see. The black hole's gravity is so strong that it bends the light from the background stars into this sort of trippy pattern as they go around each other. And a couple of my students were involved. Here's some of their pictures. One of them Haroon got to meet Ed Royce and tell him about the research that he was doing in our group. And I've got to give Ed Royce a lot of credit because Haroon had a little poster with him describing the work, and Ed sat there and read the whole thing very patiently. And then he wanted to know a little bit about what we were doing. So this is the kind of thing that leads to those waves that we saw the first time. So that's what we saw in 2015. And right away, this was a huge discovery. This told us that it wasn't just the first detection of gravitational waves. It's not just that we did something first. It's that now we have a new way to observe the universe. And there were surprises right off the bat. Until we saw these waves, we didn't know that black holes 30-some times the mass of the sun existed. We'd never seen them before indirectly by seeing light fall into them. So when I used to give this talk, I would say, well, black holes are typically a few times the mass of the sun, maybe 10. And then once we saw this, I had to go back and change those slides and say, well, now they can be, tens or maybe close to 100 times the mass of the sun. This is also the first time that we saw 2 black holes crashing into each other. No one was sure that ever happened, that conditions in the universe led 2 black holes close enough to each other that this could happen. And this let us test Einstein's theory in a way we never could before. Einstein's theory of relativity describes the solar system really well. But the solar system's gravity isn't so strong, and everything's kind of calm. It's like having a theory of water that works great on a nice calm lake on a nice sunny day. This is saying that our theory of water works even in a hurricane. This is like a storm in space-time. Now that's not the only thing that we've seen. This is an animation from another one of my students, Teresita. This is showing the waves, and if you look closely, you'll see 2 wave cycles every time they go around once of the different black holes we've seen so far. They come in different shapes and sizes. There are some bigger ones, and there are some smaller ones. Let me play it one more time. Here you can't even see the second black hole, it's so small on the screen, but there's a little tiny one going around there. This one we saw, it's dated December 26th, that's the time in Europe. In the US, it was Christmas evening, and it was my first Christmas with my wife, and we were about to go out on a walk, and so I did what any nerd would do, and I checked my email that night, just like I shouldn't have done, and I saw all these emails like, whoa, did you see this? Do you think this is a second gravitational wave? So so that was one of the things we could talk about on that walk. Then the detectors shut down for an upgrade and came back in 2017, and we saw 3 more pairs of merging black holes. And this is starting to reveal to us not just, okay, 2 black holes merge, but by looking at the patterns in the waves, we can start learning what kinds of black holes are out there. How big are they? How much mass do they have, for instance? And you might have seen in the news last year, 3 of the pioneers of our field who kicked off this whole push to measure gravitational waves, before Josh and I were born. They started thinking about how you could really do this. And this is Kip Thorne and Barry Barish and Ray Weiss won the Nobel Prize for Physics a year ago.
Wait, so some of you may have seen Kip Thorne or know Kip Thorne. So he made the movie Interstellar, and Kip Thorne was Jeffrey's PhD advisor. He's here at Caltech in Pasadena. So Jeffrey's a direct academic descendant of Kip Thorne. Ray Weiss, the one on the left, is an experimenter, and he was the person that trained my PhD advisor. And then Barry Barish is also at Caltech, and he's someone that we meet quite often. And Jeffrey and I had a breakfast with him every day of the week for when we were in the Netherlands a couple of weeks ago, and got to talk a lot about his life since detecting these prizes. So, I don't know if has anyone met Kip Thorne. He gives a lot of public lectures or maybe seen Interstellar. You have? Great, wonderful.
Did you write a book about black holes?
He wrote Black Holes and Time Warps, which is
It's funny you mention that, because I read that book in high school, and that's what got me into physics. And I was kind of afraid to tell him because I didn't want Kip to think I was like a fanboy when I was trying to get into his research group. So I didn't tell him I'd read the book until after I had my doctorate in my hands, and I felt okay about it then.
It's required reading for our students when they enter the group, just so they have a little background in black holes, popular background in black holes before they start.
So if you want to learn a little more about black holes and gravitational waves with good pictures and not too much math, just pictures and words, that's how we have our students get started. I'll also say one of the things that I learned from these conversations with Barry Barish when we were at a conference recently is he helped convince Congress to pay for this. And I asked him, how did what was the secret to talking to Congress?
Remember, you're on tape.
And he said, oh, I guess I shouldn't be standing over here then. And he said 2 things. He said, you should tell good jokes, and you should make the person you're talking to feel like they're a part of it, and you should make sure that they're a part of it. And I thought that was good advice. Okay. Whoops, that's the laser. So in 2017, we were already really, really excited. We'd seen a whole bunch of black holes crashing into each other, but then we saw a very different kind of a wave. So I'm going to start. I guess that's just a picture. So this is time and frequency, but this isn't just an eye blink of time anymore. This is showing you 30 seconds. And you can see the frequency going up and the wave getting louder. So this is a much higher pitched and longer chirp. So if the other one was more like a whoop, this is more of a whoop kind of a sound. This gravitational wave is very different because it came from a very different source. If you look at the pattern of how the wave's frequency is growing with time in this graph, you can figure out that the masses aren't 30 times the mass of the sun. They're just a bit more than 1 times the mass of the sun. So this came from 2 objects about the mass of the sun going around each other and crashing into each other. This is a computer calculation of what that would have looked like. This was done by not by Cal State Fullerton, but by some of our collaborators over at the Albert Einstein Institute in Germany. These are the 2 neutron stars, and they're sending out these yellowish gravitational waves. But now something interesting happens. When the neutron stars crash into each other, they make this giant mess of stuff. And that mess can glow very, very brightly. It can shine in different kinds of light. And it was conjectured for a long time that maybe something like this could be so bright that it makes one of these bright flashes of gamma rays, these very, very energetic forms of light. So a neutron star merger is something that you can look at not just with gravitational waves, but also with light. So this gives you a chance not to see something invisible, but to sense or observe something in space in two completely different ways. It's like the difference between just seeing something or seeing and hearing something. So here's a little bit more about that. So here's the gravitational wave that came in, but there also were some gamma ray telescopes watching the sky at the time. And about 2 seconds after the end of this wave, the gamma rays came in. So one of these flashes happened to happen just 2 seconds later. Combining the information from how the gamma rays hit the telescopes and triangulating the different patterns that the gravitational waves made on the two detectors, you could infer, well, where on the sky did this come from? The waves can get to one detector before the other if they're coming sort of in a straight line, but if they're coming from overhead, they'll hit them roughly at the same time. So they can use that information, plus a third detector we haven't shown you a picture of over in Europe, to help us figure out where you should look. And when this happened, LIGO sent out an alert to all the astronomers that said, hey, point your telescopes over here. We think we saw something. You might see something very interesting. They meant to keep it secret. Twitter accidentally said, hey, I'm Hubble, and I'm looking at a neutron star merger that day. So it wasn't a very well-kept secret. So this is a picture of how that worked. So LIGO and Virgo together, the gravitational wave detectors, said, hey, look in this dark green region. Without that new detector in Europe, it would have been this lighter green banana-shaped region here. The gamma ray telescopes weren't so sure, but they said it's got to be somewhere in this ring right here. And all of that combined said, why don't you narrow it down? Point your telescopes in here. And sure enough, they did. Here's a picture before this happened in August 2017. This is a galaxy with a fun name, NGC 4993. And if you look between these two crosshairs, there's nothing there. But when they looked immediately after this, I'm not sure quite how soon, maybe like, within half an hour, an hour.
10.9 hours is the picture there.
That picture, okay, 10 hours. Then there's this new thing in the sky that wasn't there before that you can see with light. This is the aftermath of these neutron stars crashing together and making this big mess of stuff that glows in all kinds of light. So this was a much bigger effort than just gravitational waves in the sense that it involved a lot more scientists and a lot more equipment. These are the two LIGO detectors, and then this is where the detector in Europe is. It's in Italy. These are our gravitational wave observatories. All these light blue spots are where there are telescopes on the Earth that partner with us. So when we say, hey, we think you might see something cool over here, they'll turn and look. And up until August 2017, they'd done that a few times, but it was always just sort of a drill. Like, we haven't really, like either it was a test or, well, we saw some black holes. They probably don't give off light, but maybe look there anyway. But this time, everything just fell into place. And not just these detectors on the ground, these telescopes on the ground, but some telescopes in space turned, and they all started observing in different colors of light, in infrared and X-rays, and this whole spectrum of light. Here's just a couple pictures. This one is this brand new object in the sky in radio waves, 16 days after the neutron stars crashed into each other. And here's the same thing all the way on the other end of the spectrum in X-rays. So this has just been a field day for the whole community of astronomy. Whatever kind of astronomy you're doing, you can learn something about what this city-sized nuclear matter behaves like when you take two of them and smash them into each other. And observations, ongoing observations were happening all across all these different kinds of light. Neutrino detectors looked to see if we also saw these little subatomic particles from there. They didn't really see anything, but they're also part of the search, and they might see something as well. And if that were to happen, we would have, it wouldn't just be like seeing and hearing, it'd be like seeing plus hearing plus some third sense coming to you. So the analogy sort of breaks down. So this was the first time we'd observed something in the universe with two different senses outside the solar system, with light and with gravitational waves. This was way closer than the black holes, you know, a mere 130 million light years away, not a billion light years away like the black holes. We learned that these gamma ray bursts that we've been detecting for a while really do come from neutron stars smashing into each other. And we started to get a glimpse of how neutron star matter behaves. This is a big unanswered question in astronomy. We know something about how little nuclei on Earth behave, but it's very hard there's no other good way to measure if you took giant piles of, city-sized piles of nuclear matter, what would happen? And now we're starting to learn about that.
We even have some people in the audience that have worked on that research in the past. So on understanding how neutron stars behave.
Okay, good. Thanks for pointing that out. I'll be sure to deflect all the neutron star questions that way because I mostly think about black holes. Okay, so that brings us to the present, and now Josh is going to wrap up and tell us about, so that's what we've done now, so what's next?
Okay, sure. So 4 years ago, we hadn't detected anything. Now we've detected black holes smashing together, proved Einstein's theory right. Some of our friends and colleagues have won the Nobel Prize. Big whoop. What's next? What are you gonna see next? What can we do with the future? So we've shown black holes crashing into black holes, and we've shown neutron stars crashing into neutron stars. So one thing we haven't looked at is what happens if a black hole and a neutron star come together. So right now in our center, our students are studying for a midterm, but if they weren't studying for a midterm, they would be doing computer simulations about what happens when black holes and neutron stars come together, because we're going to try to look for those in the upcoming runs.
Well, the computers keep running while we're studying.
Computers are running. So here are two of our students, Jennifer Sanchez and Vicki Brown. Jennifer is a physicist, and she's using supercomputers to calculate what happens when a black hole, which is white in her drawing here, tears apart a neutron star. Vicki Brown is an art and computer science student. So we've started working with students that are from outside of physics because they bring a lot of new abilities to bear in our research. And so Vicki has an artistic bent, but also a computer science knowledge. And so what I'm going to show you first here is the actual simulation that was done by Jennifer, which includes the physics of what happens when a neutron star gets torn apart by a black hole. And then later on in that example, when the neutron star is all dispersed out, and we would be measuring gravitational waves from this. So what we did is took the data from the physics calculation on the computers that Jennifer and Jeffrey's group did, and we gave it to Vicki so that we can start to visualize that using all of the CGI enhancement, but using the same physics that you might have in something like a Hollywood movie. And so this is just a 2-second still of that on repeat, because this took something like a few weeks to generate because of all the rendering that had to be done. And this gives us some amazing view of what happens when a neutron star gets ripped apart by a black hole and is orbiting it. So what we're looking for next is black holes tearing apart neutron stars. Haven't seen it yet, but we expect it to look like that. We can see things like that because we continue to expand our range that we can see out into the universe. In 2010, not too long before we came to talk last time, we could only see out into the universe this far. Well, how far is that? What I'm showing here, these are actually superclusters of galaxies that we're able to see with our detector. So in 2010, we could see the local supercluster of galaxies, part of like the Virgo cluster. In 2017, when we started to make our detections, we were detecting things that were out to 1 billion light years. By 2020, we're going to go a few times farther out than that. So at least double, a little bit more than double. So by 2020, we'll be able to see all of these superclusters of galaxies. We'll be able to see a few billion light years away. And what is that going to mean for our detection rates? Well, first we couldn't detect anything all the way until 2015. And then we got the detectors to be just barely sensitive enough to see anything, and we've seen 6 black hole mergers and 1 neutron star, started a new type of astronomy where we can use gravity to measure things in addition to light, cooperated with hundreds of telescopes to observe some of these things. Right now, we're doing detector upgrades to reach this larger sensitivity. In 2019, just after the holidays, we are going to expect that we get about 1 detection per week with our new detectors. And then as we make them better, we're actually going to get 1 detection per day. And at that point, it starts to be really a machine that's a discovery machine, seeing things all the time. But I would claim that even a detection per day is still not really where we want to get to. And we can draw a parallel with Galileo. So Galileo in 1600 invented the telescope and turned it toward the skies. So this is one of the first pictures that Galileo drew. Does anyone know what that picture is of? Yes.
It's supposed to be the orbit of the moon around the Earth.
This one? So the moon is definitely something that Galileo saw. So Galileo saw not only our moon and the craters that were happening on the moon, but the moons that were orbiting around Jupiter. But this particular picture is another thing, which disproved the theory that the Earth could be at the center of the universe. So what he observed here are the phases of Venus. So Venus, one of the inner planets, undergoes phases as it goes around the sun, which is something that it couldn't do if the Earth was at the center of the universe. And the phases of Venus are like the phases of the moon. And by observing those, he helped make a transformation in astronomy. So he showed us that the sun has sunspots, that the moon has mountains, that other moons orbit other planets. And that led us on a reformation. We think that we can do something similar with gravitational waves. The detectors that we have now are just barely sensitive enough to detect gravitational waves. Jeffrey showed you, here's the noise of the detector. Here's a little bit of signal peeking out of it. We're so happy we measured the first gravitational waves. But what if we made our instruments as much more sensitive as today's giant telescopes are compared to what Galileo's little 4 times telescope was? What would be able to see then? We would be able to see black hole mergers out to 6 giga light years. So I'll talk about that, what kind of distance that is in a second. Neutron stars out to 1 giga light year. So we'd be able to see basically every black hole and neutron star in the entire universe when they collided. This would be a completely new way of measuring cosmological parameters. We could start to answer questions like, were there more black holes in the past? Are there more black holes now? Is space the same in that direction as it is in that direction? And in order to do some of these things, we need dramatically better detectors. So this is Galileo in 1600. This is us in 2015. Now compare what modern astronomy can do, and we'd like to go there with gravitational waves. So how can we improve the detectors? I mentioned that the ground shakes. In Pisa, they have the Leaning Tower of Pisa. That actually is one of the inspirations for the Italian gravitational wave detector's one of its greatest centerpieces, which is that its suspensions are made on 20-meter tall pendulums with many, many stages suspended by wires, and at the very bottom of that is hung a mirror. These multiple pendulums reduce the ground motion so much that the mirror is sitting basically still at the very bottom. You could also build the detectors underground, where the ground shakes much less and there's much less wind and surface waves. Or you can sense with seismometers all around. You can sense the ground and then push the opposite way on your detector to cancel it out. So those are some ways to reduce mirror motion. What about the fact that I talked about thermal motion? So zoom way in on the front of this mirror where the laser beam is going to hit. If you zoomed in on that, it might actually look like this. The molecules would be teeming about in something called Brownian motion. What can we do about that? Well, one of the things we do when we measure this with a laser beam, if I shine a laser beam at this measures locally what the position of the mirror is. Well, if it gets hit by one of these things going forward or back, it has a noise. If I make the laser beam really big, and some of these particles are moving forward, some of them are moving backward, some to the left, some to the right, but they're moving in random directions. If you take a really big average of things moving randomly, what do you get? 0. So if you make the laser beams really big, you can make the motions average out to 0. And that's one of the things that we're doing. Another thing that we're doing is making the mirrors colder. Because if you make the mirrors colder, what that means is that the motion of the molecules slows down. And then finally, here at Cal State Fullerton, we're working on that problem of the light. So the light comes in little pitter-patters, and we don't want to lose any. We want as much light as we can possibly have. The little mirrors, so this little mirror here is a sample of the mirrors that they have in LIGO. And we're testing at Cal State Fullerton one of the processes that we use to build these mirrors, which is heating them up to reduce some of their stresses. We're heating up the mirrors inside these vacuum chambers and watching them with lasers to see if any problems happen during the heating process. And one of the things that we think might be happening is formations of little crystals that cause the light to reflect and light to get lost in the process. So this is one of the things that our students are doing at Cal State Fullerton to help make these detectors much better. So with all this work going on, let's envision for a second not just the present, but the future. So what can really happen down the road when some of the folks in the audience are professors or engineers or researchers? What could they be working on in a gravitational wave network? So I'm talking about 2030. First of all, we're developing plans now and talking to funding agencies for detectors in Europe and detectors in the United States. The European version is called Einstein Telescope, or ET. It's going to have 10-kilometer long tunnels that are 200 meters underground to reduce some of that seismic noise. It's going to have triangular detectors and 20-meter tall pendulums. It'll probably cost €1 billion, and it probably will be, hopefully will be around in the year 2030. Here in the United States, Jeffrey and I and some of our colleagues are working on the United States next generation vision. One of those possible visions is something called Cosmic Explorer, which it turns out is also the name of a pop band, I think from, I'm not sure where they're from. That's a 40-kilometer long on-the-surface concept detector. 40 kilometer, 10 times longer than our current 4-kilometer detectors. So we would get, instead of 10 to the minus 18, we'd get 10 to the minus 17 stretching. That's very nice. It would have 320 kilogram silicon optics that are cooled down to 123 Kelvin. So cooled down by more than 100 degrees. It would have 2 million watt infrared lasers, 14 centimeter wide laser beams to do that cancellation down to 0. But a lot of R&D progress is needed for the optics, for the quantum noise from the lasers, and for taking care of all the heat that is going to happen when you have a 2 million watt laser making heat. This is also around 2030, and it's also about $1 billion that's going to need to happen to make something like this happen. But why? Well, one more thing. It turns out if you ask, well, 40 kilometers, that's pretty big. Where could you put something like that? People at MIT that we're working with have taken 40-kilometer long Ls, and they've looked around the United States and asked, where can I put the L where the ground is flat enough that we won't have to spend $1 billion just digging it out, and where people don't currently live and roads don't cross and rivers don't cross? And it turns out that in southern Texas, central Texas, some places out near the Great Salt Lake in Nevada, you can place these Ls and they kind of pile up in a bunch of distinct regions where it's definitely possible to build these detectors, just because it's the right kind of land. So we've started to look at that level into whether these things could actually be built in the United States. Europe can't do this because things are too crowded over there, so they have to go underground like CERN. So why might humans want to spend $1 billion on detectors like these? Maybe a rich philanthropist will support us, but maybe it will come from taxpayers. Well, waves from black holes and neutron stars will be there, but we'll see things way more clearly. Way farther out and way more clearly. We'll see every merger in the whole universe. How do city-sized atomic nuclei behave? We'll be able to see that in much more detail. We'll see gravity in its most extreme and turbulent conditions. Some of the other exciting things are, we think that if you go far enough back in time, there shouldn't be any stars. So that means the farther away you look farther back in time. Stars formed at some point. Before that, there probably weren't any stars. But there are some theories that even before there were stars that were baked in from the beginning of the universe called primordial stars. What if we found stars that have existed since the beginning of time? How would they compare to the stars that we have now? And so this is one way that we can map the history of the universe. And then finally, every time that humanity has opened up a new sense and then used it to explore the universe, they found unknown things. So that's probably the most exciting thing for us, but it's the thing that we can least put down on paper to describe, which is we hope that we're going to see something that none of us have thought of yet. And I've been doing a lot of reading about this, and I was very surprised to learn that in astronomy, most of the major telescopes that are out there are now known for a discovery that isn't what the people who designed them put in the funding to get it funded. They're now known because they discovered something else than was anticipated. And we hope that that would happen with our detectors as well. So we've talked a lot about ground-based detectors, but to look at the entire spectrum from high frequency down to very low frequency detectors, down to very low frequency gravitational waves, we'd have to put things in space. We'd have to use pulsars or telescopes at the South Pole, which we talked about in our 2014 talk. And the ground-based interferometers are the ones that are up at the high end of the spectrum, which is a little bit more like our visible light equivalent. And so this is the picture of what gravitational wave discovery could look like in the coming decades across all bands. So I want to thank you all, and Jeffrey and I are available for any questions. The last thing I wanted to show you is just some of our students in Italy, Kip Thorne opening our center, all of our students here at my house for a barbecue. There's my daughter. I'm wearing a barbecue shirt. This is Jennifer with her simulation, Ed, Royce, and Haroon. Here are two of our students at the LIGO Livingston Observatory doing some work. Here at Disneyland, you might notice, and this was a press conference when we announced the first discovery. So there's a lot of fun things happening at Cal State Fullerton, and I want to thank you all very much for being so patient, and hope you have some questions.
How long does it take to make an animation of the black holes colliding?
Well, it depends on a couple of things. The simulations themselves, depending on how accurate you want them, can take, on our supercomputers, maybe a week or two to a month. And after you've run the calculation, then just rendering the movie might take a day, but actually designing the movie and tinkering with it to make it just the way you want, probably another couple of weeks after that. So maybe a month and a half from, oh, we saw something, to having a movie that we can show people.
Yes?
You said that you could look back in time a giga light year. So you're talking about 1 trillion light years. How is that possible if the universe is only 13 billion years old?
Well, you're gonna.
And what would you even see?
You're gonna make me reveal a hidden slide. Let's see. Where do I have to go for this, Jeffrey? Do you remember?
Well, you could try the light table.
I think it was pretty far up here. No, because it's hidden. Hidden slide. There we go. Okay, hidden slide. Oops, gotta unhide it. It's dangerous for when I leave it in the next talk. So, if the universe, so this is the distance in gigalight years, and there is something called a look-back time, and then there's something called a co-moving distance. So the look-back time is the actual time that a photon has traveled since it was emitted. But since the photon was emitted, the actual amount of time that it can take to travel to us is only 13.7 billion light years, the age of the universe. But since it left that spot, the object that created it has kept on moving farther and farther away from us. So you can ask so there's two ways you can calculate how far something is from you. You can calculate how far it was from you when it emitted the photon, or how far it is away from you when you received the photon. And since it continues, the space it continues expanding, we use the version of how far it actually is away from us now. And so that's something called the co-moving distance. That is the physical distance to that location, which has a maximum of 47 billion light years, and that's something called the observable universe. And so it's just, yeah, so it's, does that make sense? Is that helpful?
Okay. Okay, yeah.
So another thing is the giga prefix means billions. So I think you might have said trillions earlier.
I wasn't sure.
But it's
trillion or 100 billion.
Yeah, so a giga light year is a billion light years.
Right.
So
Yeah,
there's
sorry
this
about that.
effect to like 40 billion light years, but we're not expecting to see anything a trillion light years away, because anything that far away, the gravitational waves and light haven't had time to get to us yet.
Right. That's what I was wondering.
Yep. Okay, great. So I'm gonna re-skip that one so I don't accidentally. Any?
You had a quick question?
Yeah, a few actually. I remember hearing an earlier talk about LIGO, the importance of whether the two LIGO detectors were parallel or at right angles to each other, and there's a specific, there were specific advantages to both, and I've forgotten that, so I was wondering if you could remind me of that.
Yeah. So if so the gravitational wave detectors have sensitivity that is, if you ask where could you see the gravitational wave if it was coming from, if it comes like this and it's oriented so that it's stretching and squeezing like this, the detector can see it very well. But if it comes like this, where it stretches both arms the same, the detector has a sort of blind spot. And you can make a graph which shows the sensitivity for different directions, and it looks a little bit like a peanut for the gravitational wave detectors. So it's good sensitivity here and here, but not so good along this direction. Now, that means if you have two detectors that are not perfectly aligned, then if you have a gravitational wave coming from some arbitrary direction, that one of them is probably going to see it, because its blind spot is not going to line up with the other one's blind spot. So that would be an argument for why you want them to not be aligned. On the other hand, if you have them aligned, then you will always see a kind of similar thing in the two detectors. So you might get, for some orientation which is really optimal, you might get a really good measurement by both detectors at the same time. But it turns out that there's even another thing, which is we want our detectors to be pretty far away on the Earth, and the Earth is curved. So even if they're pretty much lined up, the Earth is curved enough that it sort of breaks them up in their alignment, breaks that apart enough that the blind spots aren't going to line up that much anyway. So ours ended up being almost anti-parallel. So one's pointed up and the other one's pointed kind of in the opposite direction down, which works out pretty well. Yep, great question. So maybe we'll come back to you. We have one question here, and we'll come back to you after. Yeah.
I have a book I'm going to read. I promise I'm going to read it. But it says the Big Bang never happened. Do most scientists believe in the Big Bang, or is that a... Because the book that I have, it says the Big Bang never happened is the title of the book I have.
I think that most scientists believe that the evidence is overwhelming that the universe was once smaller and hotter than it is now.
Okay.
And so the idea is that so right now the universe is expanding. And so it's getting farther apart and cooler.
Okay.
And if you play that video backwards, it would get closer together and hotter.
Right.
And so if you play that all the way back, then maybe it was a very close together, very hot state. But we're blocked from seeing we're in many ways with light and other forms of astronomy that we have currently, we're blocked from seeing the very earliest moments. So it seems like all our evidence overwhelmingly supports hotter, smaller start than we have now. So that would be what I'd say.
I think the Big Bang Theory, that phrase can mean a few different things in varying degrees of accuracy, of confidence that it's realistic. So this idea that the universe is expanding, and that when it used to be smaller and hotter, and when it got cool enough that protons and electrons joined up into atoms, light could take off and travel. We're confident about that because we see the microwaves from that today.
Right.
We see that light. What happened even earlier, because the universe was opaque then, light couldn't travel, like Josh was saying, that's more speculative. And then, and you know, we have some ideas, but there's some alternative ideas that scientists still take seriously. And then if you want to get farther from realism, like the Big Bang Theory TV show, that's probably where I put that on the other extreme.
Okay.
So yeah, let's come back to you. I think you had a second question.
Yeah, a brief question, because
Nice to
wormholes
meet you.
were
Bye.
a brief question because wormholes were mentioned earlier. Is there any possibility that a wormhole could occur naturally? I mean, I'm pretty sure that's fairly slim, but is there any possibility? And would creating them, let alone maintaining them or making them safe, be artificially feasible?
Well, not anytime soon. There's a couple of problems.
Thank
They're
you.
probably impossible. The problem is they tend to collapse really fast, and you need matter that basically it would have to have gravitational repulsion, so the mass
Thank
would be
you.
negative. We're pretty sure we don't have any such things in the universe. But supposing you had that, it also can be hard because it takes a lot of, because they're unstable, so you disturb them a little bit and they still collapse. But even if you could get past that, then the last problem with wormholes is it takes so much energy to create a significant amount of curvature. The kind that we're just barely able to measure the waves from are these like giant black holes And we're nowhere near manipulating those kinds of energies that'd be required. So at best in the far future, but probably they're not possible in the real universe. But that said, no one's proven you can't do it. So there's still hope for everyone making sci-fi movies of good and dubious quality using them. Yes?
If dark matter has any black hole analogs, and there's collisions between objects like that, do you have any sense of what the signal would look like if it showed up?
That's a really good question. So we're not sure what dark matter is. If there were clumps of it in the same kinds of masses as black holes that orbited each other, it might be hard for us to tell the difference. Like we haven't observed it. The only thing we've observed that many solar masses is a black hole. So I'm not an expert on dark matter, but I've talked to some colleagues who know something about it, and most scientists think that black holes probably aren't dark matter, and they're dark, but they're not. The dark matter is this stuff that surrounds galaxies that we can't see. We don't know what it is, but we can tell by its gravitational effect on the visible matter that we do see. And the problem is we think that just like in that movie I showed where the black hole's gravity was so strong that it bent the light around, that if dark matter, when there's so much of it, was made of black holes like this, that it'd be given away by this kind of lensing effect. So we're pretty sure it's something else because of that, because we haven't seen this lensing that would give it away if it were black holes, but we're not completely sure what it is.
Ken?
I've always wondered when trying to sell like the LIGO idea, usually members of Congress, aren't with it, scientifically, and hey, we'll spend $1 billion for this idea for something that may or may not happen. We're not sure. As a part of that, I always wondered, since they're so sensitive, if you can say something about it, but can you say like, sure, we'll look for gravitational waves, but they're so sensitive that we can pick up what's happening to Earth, and hey, if North Korea lights off something, we can kind of, we might be able to tell you something about it. So, does that happen? Has that happened, or is that part of the selling process?
That does happen. I don't believe it's part of the selling process, because as great as our detectors are at measuring gravitational waves, we try very hard to isolate them from the ground. And we do that by using seismometers that are all around. So we have a very good array of seismometers, and they can measure nuclear tests and things like that. But our array of seismometers is not better than the USGS's array of seismometers, which they have arrayed all around. And so our measurements there are a little bit duplicative of their work. We can, the other types of things that we can measure are not really, are all in the realm of physics. We can use gravitational wave detectors to measure other types of physics, like something called a Shapiro time delay, or something like we might try to measure different types of particles called axions and stuff, but that's all in physics, so it's not going to help turn a military-minded congressman, for example, on our project. What our project does have is really big lasers, a lot of laser technology, a lot of advancements in optical technology, and those technologies are very strongly tied to industry and to defense and other areas. So some of the advances that we might make in optical coatings could actually lead to advancements in those areas. Yeah, so it's a very good question, which we're thinking about too, which is capturing the public and our lawmakers' attention, and how can we get people excited about this, or as excited about this as we are. And that was once done. Jeffrey's looked into that a little bit for when the original LIGOs were funded.
Yeah, I think, I agree with everything that you were saying. I think when you say, a question that often comes up is what practical use is any of this, and that's something that Congress people might ask. And there's a couple of things we like to tell people about that. One is that it took about 100 years from Einstein coming up with this theory of relativity to building the global positioning system, so that we all use when we get directions on our phone. But it turns out that system doesn't work without the corrections to gravity from relativity. But that was never the intention. So, you know, at about 100 years out, we don't know what technology might try to do with the things we're doing. But the other thing that we like to say is, not only can sometimes you have some technology that you share that's more practical, like making better mirrors or better laser